What's up, y'all? I'm Mindful, back with part 2 of the Paradox and Thought Experiment Iceberg. In this video, we're going to be covering layers 3 and 4 of this iceberg. If you haven't already seen part 1 of this video, I will leave the link to the description to go check that out, as I recommend watching that before you watch this. But anyway, we're going to jump right into it. I'm not going to waste any time, so let's get into it. So the first entry is the ant on a rubber rope. And the ant on a rubber rope is a mathematical puzzle that states an ant starts to crawl along a taut rubber rope 1 kilometer long at a speed of 1 centimeter per second. At the same time, the rope starts to stretch uniformly at a constant rate of 1 kilometer per second, so that after 1 second it is 2 kilometers long, after 2 seconds it is 3 kilometers long, etc. And it goes on for infinity until it's infinitely many kilometers long. Will the ant ever reach the end of the rope? So you would think that since the rope is expanding much faster than the ant will never actually reach the end of it. But this isn't true. So yes, the ant will reach the end of the rope in approximately 8.9 times 10 to the power of 43,421 years. It's a while, but he eventually does get there. And that is because the rope is stretching uniformly at a constant rate on both sides. So once the ant reaches the halfway point of the rope, like the initial rope, the distance, while it's still increasing, will continue to get exponentially smaller. Now, in real life, this would never occur and never happen because that length of time is so big that it's just a thought experiment, and it's interesting to think about. So the next entry on this list is Maxwell's Demon, and I'm going to actually refer to this as Maxwell's Demon, as that was the original intention by William Thomson when he used the word daemon to describe this. So this is a thought experiment that hypothetically breaks the second law of thermodynamics, which states that two bodies of different temperatures, when brought into contact with each other, will come to a thermodynamic equilibrium and both will have the same temperature. So here, Maxwell proposes a system where there are two gas chambers right next to each other, both at the same temperature, and a daemon in between controlling both a door that will let faster moving particles into one side and slower moving particles into the other. So he will be increasing the temperature of one side while decreasing the temperature of the other, and the part that is violating the second law would be the fact that the daemon is decreasing the total entropy of the system without applying any work. There have been proposed explanations to this where someone has stated that the daemon would have to store or erase information on the particle's speed, therefore creating more entropy than what his action is. But this is a theoretical though, as most scientists have argued that any practical device of this kind would be capable of violating the second law of thermodynamics. Alright, so the next is the uncertainty principle, and this one is a quantum mechanics one that deals with a whole bunch of math symbols and concepts that I don't really understand, but I'm going to try to lay it out in simple terms. So the uncertainty principle, again, super simplified down, states that the more precisely you know a particle's position, the less precisely you can know a particle's momentum, and vice versa. This is talking about like protons, electrons, and photons and all of that, not like just individual atoms. So these are very small particles. Again, I don't really know a whole lot about quantum mechanics and what would this be used for, but from my research, this is a fundamental thing to understand anything about quantum systems. So the next entry is Lepley's Demon. Again, this one's kind of like Maxwell's Demon, where it deals with laws of thermodynamics. And again, the creator of this theory, which was French scholar Pierre-Simon de Laplace, I'm sorry if I got that name wrong, does not refer to this being as a demon, but instead was later added on in translation. But I'll use demon for this one. Anyway, Laplace theorized that according to the principles of determinism, a demon who knows the precise location and momentum of every single particle in the universe, that demon should be able to know every particle's past and future values, therefore knowing exactly what has happened in the future and exactly what has happened in the past. This was written in 1814 and since then has been disproven with what we know now about the laws of the universe. For example, the 19th century concepts such as irreversibility, entropy, and the second law of thermodynamics are used to completely debunk this idea, as the original was based on reversibility and classic mechanics. There are other theories that debunk this, such as quantum mechanical irreversibility, chaos theory, and Cantor disorganization, so this thought experiment is an interesting one, but wouldn't work out with what we know now about the universe. Alright, so the next entry is the Bootstrap Paradox, and this isn't just one paradox, but instead is a blanket term used to describe multiple different time travel paradoxes that involve items of no original origin. So this happens when any event, whether it be action, information, object, or person, ultimately causes itself. An example of this was used in the movie Somewhere in Time, where an old woman gives a watch to a young man, and the young man eventually travels back in time and meets the same woman when she is significantly younger. This young man gives her the watch, which eventually will be the same watch that the old lady gives to him. Therefore, there is no origin of this watch, and it exists somewhere in space-time where no one would exactly be able to figure out where it is. The next entry is the dark sky paradox, and this one is an astrophysics example that says that the darkness of the night sky should be in conflict with the assumption of an infinite and eternal static universe. This theory states that since there is an infinite number of stars in our galaxy and it's an infinitely expanding universe, every sightline from Earth should theoretically end in a star, so the light emitted from them should make the Earth way more brighter than it is now at night. Another thing with this is that stars are constantly being born and dying at the same time in our universe, so some points would, at some point, not have a star that is emitting light to them because there either is a dead star there or there is a young star whose light has not yet reached Earth due to the limitations of light speed. So this theory pretty much disproves the idea of a static universe. So the next entry is the stability-instability paradox, and this one's actually interesting because it doesn't deal with any space or any of that kind of fun quantum stuff, but this one actually deals with politics. Yeah, politics. But it's about the probabilities of war and mutually assured destruction. So this principle states that if two countries have hostile relations and both countries have nuclear weapons, the chance of war between the two significantly decreases. However, the chance of minor or indirect conflicts between the two drastically increases. The principle was seen in effect in the Cold War, where America and Soviet Union were at odds with each other. While they never actually engaged in warfare with each other, they did fight proxy wars in events such as Korea and Vietnam. This paradox should be in case most of the time. However, the only thing it assumes is that each person acts rationally. A counter-argument to this is where something like a government with a theocratic leader, where they believe that the afterlife is significantly better than our current life, and therefore should make a swift transition for as many people as possible to that afterlife. So the next entry is the unexpected hanging paradox. This one you guys might have heard before, and it's a paradox that deals with the certainty of uncertainty of future events. So, this paradox goes as follows. A judge tells a prisoner that he will be hanged at noon on one weekday the next week, but the execution will be a surprise to the prisoner. He will not know until that day. Using just that sentence, the prisoner should understand that the hanging will not be a surprise, and therefore the judge is wrong. The prisoner realizes that the hanging cannot be Friday, because if he has not been killed by noon on Thursday, then he knows that it will happen Friday. Then he realizes that if he isn't killed on Wednesday, since Friday has already been eliminated, then Thursday has been eliminated too. And by that logic, the prisoner can use this to know that he will not be hung at all because all possible options, all days of the week, have been ruled out. However, the executioner knocks on his door on Wednesday, despite all of the above being true, and the prisoner is surprised. The prisoner never knew what day it would happen because since he could eliminate all the days that he could be hanged on, then he theoretically should never be hanged. Simplifying this down further can lead to understanding that instead the judge says to the prisoner, "You will be hanged tomorrow, but you do not know that." So the next is Hooper's Paradox, and Hooper's Paradox is a geometrical fallacy using the reorganization of triangles and parallelograms. The image should be on screen to help you guys visualize this one, but basically Hooper stated that moving these shapes around would create the loss or gain of two geometric units. However, it has been debunked as the whole overlap between the triangles in the first image has been found out to be what those two missing units are. So this one is a false paradox. So the Gabriels Nelson Paradox is a paradox that concerns the applicability of the word heterological. So in this you have to understand two words, autological and heterological. Autological means a word describes itself. For example, the word pentasyllabic is autological because the word is describing itself. Heterological means a word does not describe itself. For example, monosyllabic is a heterological word because that word has more than one syllable. So, it is reasonable to assume that all adjectives should fall under one of these two categories. But they actually do not. So, now we should take the word heterological. Is it itself a heterological word? If it is, then it does not describe itself, therefore it is not heterological. If it is not, then heterological does describe itself, and therefore it is. So this word cannot be placed in either of the two categories. There are some other cases like this, like for example, if you how you say the word loud. If you say it loud, then it's autological, but if you don't say it loud, then it's heterological. There's a bunch more linguistic paradoxes like this on this iceberg, but this is just one that is a paradox on words and basically what they mean. So the Klein Paradox, this is another one of quantum mechanics that I'm going to try to simplify for you. If you guys have ever seen the Flash TV show or know what phasing is, this is pretty similar. So in this experiment, electrons are shot at a barrier, such as a wall or something. But using logic, you should expect for the electrons, like any normal particle, to theoretically hit the wall and bounce back with like force, much like a ball. However, there's a possibility that the particles actually go through the wall because of certain quantum properties that makes a scenario in which they can tunnel through the barrier. I don't really understand how this is possible. I don't really understand how this is possible, but it apparently is. So Bell's theorem is another quantum mechanics one I don't really know how to explain, but here's my best go at it. So this is a concept that deals with the nature of small particles when they are entangled, which is when two particles have a connection where the state of one particle is directly related to the state of another. So if you measure them, measuring like is something like the particle spin, and using classic physics, the particle of one should not affect the other because information cannot travel faster than the speed of light. So, if you measure them in different ways, this creates a scenario in which it cannot be explained by classic physics and violates what is known as local realism, which is the idea that each particle has definite properties before you measure them. Basically, this theorem just shows that entangled particles can't be explained by normal everyday physics and only by quantum mechanics. The Faraday Paradox was a once unexplained chemical reaction discovered in 1830. This occurred when scientist Michael Faraday found that diluted nitric acid would dissolve steel, but concentrated nitric acid would not. This later would be figured out to be due to the concept of passivation, which is a chemical layer around something that will make it less harmed by its surroundings, which also helped to lead to the discovery of electrochemistry. So I couldn't really find a whole lot on this one, and from what I did find, it was kind of bland, but I'm just going to give it to you anyway. So the right angle paradox states that suppose you have a right angle lever where the bend would appear to violate the principle of conservation of angular momentum. When a force is applied to the lever, the angular momentum would seem to change, although there is no external torque acting on it. Basically, right angle levers can't exist due to physics. So Aristotles Wheel is a paradox stated by Aristotle, where you have a wheel, or two circles, one with a large circumference and one with a smaller circumference that is inside the larger one. The wheel then travels a distance that is exactly equal to the circumference of the larger circle. However, you would find that the smaller circle has also traveled a distance that is equal to exactly one circumference of the larger circle's worth. So, how exactly does the smaller circle travel the same distance when the circumference is way smaller than what the larger circle is? Aristotle's proposed solution to this is that motion is actually continuous, and for the wheel and all parts of it to be moving together simultaneously. So, Aristotle's proposed solution to this is that motion is continuous, and for the wheel, all the parts are moving together simultaneously, and there's no part that is moving before another. So the heat-death paradox is a paradox that was used to disprove the idea of an eternal universe, that everything is always there and always has been. Using the second law of thermodynamics, this paradox believes that everything eventually in the universe would have leveled out in a form of temperature. This is because the universe will either reach a point where there's no stars, or everything is as hot as stars. Therefore, the idea of the heat-death of the universe. To disprove the eternal universe idea, Lord Kelvin pointed out that since there are things going on right now, the universe has not reached its heat death yet, and if the universe was eternal, then it would have reached its heat death a long time ago. So the Impba Effect, I'm sorry if I got that name wrong, but this is the contradictory idea that hot water can freeze faster than cold water while under the same effects. This effect has been documented in several experiments, but it has never been able to be consistently reproduced, and a true cause to this effect has still yet to be figured out, as it is hard to pinpoint exactly what the constant that causes it is. Alright, so the Archer's Paradox is a phenomenon that occurs when dealing with an ordinary drawstring bow. When the archer draws a bow, it is initially pointed to the side of a target. However, when it gets released, the arrow will get flexed around the bow and then straighten out towards the target. The paradox is where the arrow points and the final trajectory that it takes due to the flexing of the bow. Modern archery, like a compound bow and certain arrows, mitigate this effect, but it's still interesting to think about because not all shots you take with a bow are ever going to be 100% accurate. Alright, so the Bartender Paradox, this one was a little bit hard to find information about, but I think this is referring to another time travel paradox that actually is pretty insane. So in this one, an orphan girl is abandoned and left in 1945. Years later, in 1963, she goes to a bar and is attracted to a drifter. She gets pregnant, and when she is having delivery, the doctors discover that she has both sex organs. In order to save her life, they keep the male organs, and to make matters worse, the little baby gets kidnapped. This person, now in 1970, goes into a bar and tells the story to a bartender. The bartender then offers the person the ability to join something called the Time Traveler's Corps. They then go back in time to 1963, and this person falls in love with a young orphan, and that orphan gets pregnant. The old bartender, however, went forward in time 9 months ago to kidnap the girl that the two had and drops the girl off in 1945. The bartender then drops him off in 1985, and this person joins the Time Traveler Corps. After a while, this person then goes back to 1970 and works at a bar and is told the same story he had years earlier. I left out a lot of this, but this is a very simplified version that you should be able to understand. This person was originally named Jane by the original creator, and she is her own mother, father, grandfather, grandmother, daughter, and son all at the same time. Again, this is a rather confusing one, but it makes sense in the case of time travel. This one kind of calls back to one I mentioned earlier in the tier, and that's being the Bootstrap Paradox, where this individual has no origin and henceforth exists somewhere in space-time. So the next one is China Brain, and I don't know what it is with all these thought experiments using Chinese people as their subjects, but China Brain is very similar to the Chinese room experiment I mentioned earlier in the first video. In this thought experiment, it asks every Chinese person to simulate one neuron in the brain, using like telephones or something to communicate, much like how our brains use axioms and dendrites. It then poses the question if this brain of the Chinese nation would have a mind or consciousness or something of that sort the same way our brains do. And also, could a mind exist inside of a larger mind? The brain possesses all the workings of a single brain and should therefore have a mind of its own. However, it is thought that it shouldn't at all have a consciousness despite having all of the functions of a brain. So the next entry is Quantum Immortality, and I find this one super interesting, and it was actually the main inspiration for the making of this tier list. So this is a version of Schrodinger's cat that I mentioned earlier in the Iceberg, and this theory should be able to falsify most of quantum mechanics if proven true. So in this situation, it's kind of the same thing that happens with Schrodinger's cat. The only difference is now the observer is in the box and not the cat. So much like the cat, the person's fate is linked to a subatomic fate, and they should therefore die eventually just due to the odds of the situation. This one also has multiversal implications too, but say the odds of you dying every second are about 50-50. If the multiversal theory is true, there will always be a world in which you live. So if the experiment is performed 50 times, at that point the odds are so astronomically low that you would be basically guaranteed to die, but at the same time there's always a universe in which you live. The immortality point comes when you consider dying of an old age. So say you are on your last breath. There will always be a universe in which you have another breath. Your consciousness has never known death, and therefore would be in the multiverse where everything goes exactly perfectly for you to never take your last breath. So for all the people that have died that you know of, if the multiversal hypothesis is true, then there's another universe in which they are alive, where their cause of death never happened, or they are the immortal being in that universe. I've always found this one kind of interesting, and personally, I kind of believe it, but however, you really can never know if it's true, because the only point where you will find out if that's true is either you die, or you become so old that the only way you are alive is because of this idea. So the next is the balls and vase problem, which is a hypothetical math problem that is designed to test the nature of the mathematical concept of infinity. The test goes as follows. Suppose you have an empty vase and an infinite number of balls. Then an infinite number of steps are taken so that 10 balls are added from the vase and 1 is removed to it. To use this test, we have to put a time limit on it. So say we're going to say that the first step is performed 30 seconds prior to noon and the start time is 1 minute before noon. Each step is performed in half the time of the last one, with the second step being 15 seconds, the third being 7.5, and so on to an infinitely amount of smaller numbers. So by the time 1 minute has passed, an infinite number of steps has occurred, and you must therefore ask, how many balls are in the vase? The easiest answer to this is that there are infinitely many, considering an infinite number of balls has been placed in the vase. However, there's a solution that proposes that there is actually no balls in the vase, and this goes as follows. Suppose we give every ball a number 1 through infinity. With the first step, you would add balls 1 through 10, with ball 1 being removed. For the second step, you would add balls 11 through 20, with ball 2 being removed. You can use this logic to infinity to realize that by the time it's noon, every single ball would have eventually been removed if an infinite number of steps has occurred. So the next entry is Flatland, and Flatland was a book written in 1884 and was intended to be a comment on Victorian culture, but it is instead known for its examination of dimensions. I kind of mentioned this idea in the Limit of Knowledge video I posted before I started this iceberg, so I recommend you check that out after you watch this video if you haven't already seen it. With that being said, this book starts with the main character, who is a square, who lives in a two-dimensional world called Flatland. In this, he tries to communicate with the inhabitants of a place called Lineland, which is a one-dimensional world, and its inhabitants are points, and finds that they have trouble understanding what the square is trying to communicate with them about his two-dimensional world. Next, the square is visited by a sphere from a place called Spaceland, which is a three-dimensional world, and the sphere tries to convince the square of what the three-dimensional world is and that there are other dimensions. Much like the points in Lineland, the square is actually unable to understand what he's saying despite the sphere's best efforts. To take away from this, we live in a three-dimensional world where we can see everything in 2 dimensions and 1 dimension, but if we were to try to explain the three-dimensional world to either one of them, they would not be able to understand it. It would be the same as if we were visited by some 4th dimension entity, which we wouldn't be able to understand and will never truly know how many dimensions our universe is. The next one is the brain in a vat thought experiment, which I'm sure many of you have heard of or at least thought about it without realizing it. But this one focuses on one of those weird simulation theories that, again, you could go down a massive rabbit hole of arguments and counter-arguments for, which I will not go into in this video, but I actually may make another one on just this topic. Anyway, this idea states that suppose you have a mad scientist who has cut someone's brain out from their body, put it in a vat of liquid that keeps the brain alive, and has wires connecting it up to a computer. The computer then uses the brain to simulate reality, while the brain acts in its new alternate reality just how it would believe in the original. So, if this thought experiment were possible, who's to say you aren't just a brain in a vat watching this video? Alright, so the next entry on this list is the bucket argument, and the bucket argument is an idea proposed by Isaac Newton that argues for the idea of absolute space. In this, suppose you have a bucket filled with water that is hanging from a long rope. You then twist the rope, and the water in the bucket should start rotating. Newton then would argue that if the water begins to spin without any forces on it, then there's reason to believe that there's absolute rotation, therefore there must be an absolute space in which rotation can be measured. So this was used to argue against the idea that motion is only relative, and it was also used up until the final release of the theory of relativity, released by Albert Einstein, finally was developed. The next theory on this list is the Crocodile Dilemma, and this one is kind of similar to the liar paradox I mentioned in the first tier, where this provides a statement that is both logically and paradoxically true in nature at the same time. This one states that there's a crocodile who has stolen a child, promises to return that child to the parent if and only if the parent can correctly predict what the crocodile will do next. It is simple if the parent predicts that he will give the child back because he can just run away with it and not give it back. There's no really paradox there. But the problem comes whenever they guess that the child will not be returned to them. In one situation, the crocodile would keep the child, in which case the crocodile's next move has been predicted, so he should give back the child, and in the other, the crocodile gives back the child, in which case the parent did not predict correctly, so he should not have given back the child. Therefore, the crocodile is in a paradoxical situation in which there is no possible solution. And with that, we've finished tier 3 of this iceberg, and we'll move on to tier 4. So the first entry in the tier 4 is the Boltman Brain, and the Boltman Brain is the idea that it is more likely for a single brain, complete with memories and thought and all of that, to have been generated by the void than for an entire universe. So the background behind this belief was that there was originally low entropy of the universe at the beginning of time, which that was necessary for the formation of galaxies and all that. Could actually be a statistical fluke, and because of that there's fluctuations in entropy, and it should be more likely for a self-aware brain to have been produced rather than for a universe. So if this idea is true, then our understanding of the universe might just be one of these statistical brain fluctuations, and if you think about it, you might just be a random Boltzmann brain floating in space that just spawned and you would have no idea. So all horses of the same color is a paradox. It's a false one that argues that in this experiment all horses have the same color. So we say that we have one horse where n equals 1, and we establish that if n horses have the same color, then n plus 1 horses must also have the same color. The second step is a bit confusing, but it goes as follows. Assume all n horses are the same color, and consider a group of n plus 1 horses. First, exclude 1 horses, and then look at the other horses. They're all the same color. Likewise, if you do this to another horse that is not the same one as the first removed, then all the n horses are still the same color. Doing this with all of them, you have concluded that all horses in any group must be the same color. The only problem is that the first step is logically false, as it implies that you have a group of 3 or more, when you must first have a group of 2 to start, because when one horse is excluded in a group of 2, there are no non-excluded horses, and so therefore the logic behind this paradox is flawed and therefore a falsidical paradox. The next entry is Gabriels Horn, and Gabriels Horn refers to a type of geometric object that has an infinite surface area but yet a finite volume. This was named after the biblical angel of Gabriel, where Gabriel has a horn that he blows that signals the end of the world, but this figure is formed by taking the graph of the equation of y equals 1 over x between 1 and infinity, and then rotating that region around the x-axis. The reason this has an infinite surface area is because the surface area is an integral of a summation that leads to infinity, but the volume of the shape is not, and so therefore it is finite. The next entry is the quantum Zeno effect, and this refers to an idea that, if observed, an unstable particle should never decay. Firstly, quantum superposition makes it possible so that particles such as electrons can exist in multiple states simultaneously until a measure is made on them. Then you have an idea that is known as wave function collapse, which happens whenever you measure a quantum system and the wave function of that system collapses into a single state. The effect comes in whenever you frequently measure a quantum system and you make the system collapse into its original state, therefore freezing the system in time in that state because it doesn't have the ability to change into existing ones because you are constantly measuring it. Therefore the quantum Zeno effect, and you have an unstable particle that will never change. The next entry is called when a white horse is not a horse, and this is another linguistic paradox that it follows these 3 steps. The next one revolves around a paradoxical statement that is stated when a white horse is not a white horse. So this one revolves around a paradoxical statement that says when a white horse is not a horse. The argument follows these steps. A white horse is a horse. A white horse is also white, and so therefore a white horse is not just a horse. It is a white horse. Then the creator, Gong Sun Long, I'm sorry if I butchered that name, but he adds that what is not a horse is not a horse, and therefore has come to the conclusion that a white horse is not a horse. This one's kind of like the other linguistic paradoxes on this iceberg, where people pretty much like stretch the uses of words to their absolute limit, and you come to a point where you have a paradox out of them. I don't know. I think it's pretty interesting. So the next entry is the black hole information paradox, and this is what happens whenever you put together quantum mechanics and general relativity and consider the fate of information that has fallen inside of a black hole. Firstly, black holes when formed have something known as an event horizon, and that is a point which nothing, not even light, can escape. Due to something called Hawking radiation, sometimes a particle can fall into a black hole and another escapes as radiation, causing the black hole to shrink over time. The paradox comes in when you ask what happens to the information of a particle that falls into a black hole. Using classic physics, it should be lost forever, but according to quantum mechanics, there's a principle that information can never be created or destroyed. Therefore, once the black hole is gone due to Hawking radiation, the information would be completely gone despite violating a core quantum mechanics rule. The Barry paradox is another linguistic paradox that comes from the phrase, the smallest positive integer is not definable in under 60 letters. If such a number were to exist, then it should therefore be able to be defined by the previous sentence, but the sentence claims that it is not definable in under 60 letters. If it is not definable in under 60 letters, then the statement becomes true, and then the statement itself becomes its definition. This one is kind of like the heterological and autological one I mentioned earlier, where you have words that start to define themselves and you start to create statements that cannot be true or false. The next one is Bell's Spaceship Paradox, and this one is a special relativity one that has 2 spaceships, each heading the same direction, attached by a rope. Then they start to simultaneously accelerate in an initial frame called S. This means that they have the same velocity at the same time and are subject to the Lorentz contraction, which is where a moving object's length is shorter than when it is measured at a rest frame. You would think that the rope would remain intact, however, that it's actually found to not have the same acceleration due to the relativity of simultaneity, which will lead to an increase in distance, and therefore the rope breaks. This one I don't really understand too well, so I'm sorry my definition wasn't like completely perfect. But so Bentleys Paradox is a cosmological one that stems from the theory of gravity. It states that if all stars are at one point drawn to another by gravitation, then theoretically they should all collapse into a single point. In theory, in an infinite universe, if all stars were placed perfectly by a statistical miracle, then all forces would act evenly on all stars, and therefore they wouldn't have motion and they would not collapse. This originated in the late 1600s, and so today we know now that if there was an infinite universe, then it would indeed collapse on itself, but instead there are a finite number of stars always constantly in motion that are attracting each other that leads or avoids collapse. So Russell's paradox is a paradox in set theory that shows that every set theory that has an unrestricted comprehension principle leads to contradictions. For example, consider the set of all sets. Russell, the creator of this, defines R as the set of all sets that do not contain themselves. So, is R a part of itself? If so, then it is a set that is contained in another set, therefore violating the rules. If it is not, then it is a set that is not contained in another set and should therefore be contained in itself. The next is the tea leaf paradox, which was once an unsolved mystery regarding what happens when you spin tea leaves in a cup. You would think that if you stirred the cup in the middle, then the tea leaves should theoretically rotate to the outside of the cup. However, as proven when this was solved, the tea leaves gravitate towards the bottom of the middle of the cup, which is due to something called centrifugal force, which helps friction keep the tea leaves at the bottom, since that force is weaker at the bottom than it is at the top. So the next entry is Werners Friend. I don't know if this is German or not, so it would be Wigner. I'm not really sure, but I'm just going to use Wigner as it for this video. But Werners Friend is a thought experiment in quantum mechanics that was used to explore the implications of measuring quantum systems. So I'm going to give you the setup for this. Firstly, suppose Wigner is outside of a laboratory and his friend is inside performing a measurement on a particle. Before his friend measures that particle, say an electron, the particle should exist in a state of superposition, and then once measured, that particle would collapse into a definite state. From Wigner's perspective, since he does not know the information of that particle, it should still be in a state of superposition, and for his friend, the particle should not be anymore. So, the particle is both now in a state of superposition and not, and from Wigner's perspective, the whole state, including his friend, is actually in a state of superposition. Again, quantum mechanics, I really don't know a whole lot about it, so if that made zero sense, it also made zero sense to me. So Einstein's Box was a thought experiment from Albert Einstein, once again dealing with quantum mechanics. So consider this hypothetical light box that Einstein creates. I'll have the image on screen so that this is easier to explain. So this one involves a box that had the ability to allow one photon to escape at a time. The idea behind this was that you can measure both the energy of the photon that escaped and the exact time of its departure, which Einstein believed generated a flaw in Heisenberg's uncertainty principle, which states that you cannot know both the speed and position of a particle. However, this was refuted by Niels Bohr, as he used Einstein's own theory of relativity against him to prove that the emission time of the particle was still an uncertainty. The next paradox is the Necktie Paradox, and this is a paradox in probability that states that there are two certain people, each given a necktie, and they argue over who has the cheaper one, and the person with the more expensive one must give it to the other person. The reasoning behind this goes as follows. So let's just take a look at the first person. If they lose the bet, then they lose the value of their necktie. And if they win, then they win more than the value of their necktie. Therefore, the wager is an advantage to the first person, but using the same reasoning, you could also see that the wager is an advantage to the second person. So, in this situation, both appear to have an advantage, but however, when closely examining what the meaning of the statement, the value of the necktie is, it can be reasonably understood that both actually have the same odds. So this one's a falsidical paradox. So monkey and hunter refers to a thought experiment in physics that follows a statement that a hunter is going out with a blowgun and sees a monkey hanging from a tree. The hunter is going to shoot the monkey, but the monkey will drop from the tree the second that the hunter shoots the blowgun, so where should the hunter aim if he wants to hit the monkey? If the hunter aims directly at the monkey, which kind of seems counterintuitive, as you would think that since the monkey is going to be falling, then the dart from the blowgun would just miss the monkey, since it should have fallen by the point that blow dart would reach. However, using gravity in physics, it can be reasoned that since gravity has the same effect on both objects, regardless of the acceleration and velocity of the dart, they should both fall vertically at the same time, which would lead to the dart hitting the monkey if aimed directly at it. So the next experiment is the floating man, and this is a thought experiment where suppose you have a person who who has suddenly come into existence, floating in an empty space with no sensory experiences and no senses to connect them to the world. This person can't see, hear, or feel anything that would allow them to know their environment, so the question is, would they be aware that they exist without any sensory experiences? The creator of this, who was an Islamic philosopher named Avicenna, believes that they still would be, and that the awareness of one's existence doesn't depend on any sensory output. So this one is related to the relationship between the mind and body, and begs reason to believe that if this were found to be true, then it could be rationally assumed that humans have souls. So the next one is the Swamp Man, and the Swamp Man is a philosophical thought concept created by Donald Davidson in 1987 that says, suppose you are sitting in a swamp and you are hit by lightning and therefore disintegrated, while simultaneously an exact copy of yourself is made perfectly from a nearby tree, and this copy of you we will label as the Swamp Man. So the Swamp Man would be completely indistinguishable from you and would continue on with your life as if nothing had happened. So using this idea, Davidson proposed that thought and meaning would not be able to exist in a vacuum, and that therefore the Swamp Man would not be you, but instead a blank version of you that does not have any thoughts or memories. So the next one is Popper's experiment, which is kind of similar to Einstein's box and where it is used to test Heisenberg's uncertainty principle, and in simple terms, this is how the experiment goes. A low intensity source emits a pair of particles, one traveling left and one traveling right. Then slits A and B are introduced, which are semicircular arrays placed behind them, and the arrays only let particles through if both arrays detect a particle at the same time. This is where it kind of goes into particle scatter, which I really don't know what it is, so I'm not really going to explain the experiment further, but I will tell you what happened because of it. So basically, Popper argues that this statement violates the Copenhagen interpretation, which is the fact that particles have no existence until measured, and this has been continuously argued over the years, and we don't really have any answers for it. Again, this one's in quantum mechanics, and it's very complicated to understand to like an average human being. So if you know how this one, like the experiment actually is, I would love to hear about it in the comments, as from what I have read, I cannot comprehend it. So Socrates' paradox is a philosophical thought experiment, once again dealing with a linguistic problem. Suppose you have a heap of sand. If you remove 1 grain of sand, then there is still a heap of it. Keep doing this until you have a few grains of sand left. Is that amount still considered a heap? This one is kind of like Theseus' ship in a way, where there's no direct point in which this heap has become a non-heap, and therefore it's technically both at the same time, regardless of how many grains of sand you have. And with that, we have come to the conclusion of tier 4, and therefore part 2 of this iceberg. I'm going to try to get part 3 out for you guys by Friday of next week, and then hopefully have the full iceberg video released on like Sunday. So if you guys want to see that, then it will come out then. If you still haven't seen the first video, then I seriously recommend watching that one, and I will leave the link to that in the description. This video took quite a while to make, so as always, it would mean a lot to me if you liked and subscribed. I think 90% of you guys are not subscribed, so we gotta change that number. But anyways, I'm mindful, and I hope you guys have a good rest of your day. Peace.